All right, so I'm not sure if Martin Gardner ever directly worked with applied category theory, but I think the kind of ideas it allows you to do with visualizing using these kind of diagrams to reason about mathematical concepts seems very much in his spirit. And so I'll start with talking about why we would possibly be interested in monoidal categories. They allow us to use rigorous mathematical reasoning to think about things like string diagrams, which particularly describe how things compose together. So in this example, we see a recipe for making a pie, and the wires represent ingredients or just, food in general, and we see the boxes represent operations we do on them to transform them into different kinds of things. And so this kind of diagram shows how we can think about how physical systems relate to each other and how we perform operations on them using these diagrams. And so we're talking about monoidal categories, and a monoid is a set that has both an identity or zero element and, most importantly, an associative operation. So for example, on the non-negative integers, addition is associative. This means it doesn't matter whether you group A and B together or B and C together. When you say A plus B plus C, the result is the same thing. And this associativity justifies us in writing the single expression A plus B plus C with no parentheses for the same thing. And similarly, we can apply this idea to pictures and how we draw diagrams. So if we have three systems and we apply F, G, and H to all of them, this is the same if we group the two systems on the left together and apply F, G there, and then H on the other one, and then swap the wires, or if we do the swap first and then F on the left and G and H on the right. And if you're familiar at all with category theory, this equality of diagrams corresponds to a commutative diagram in category theory. And so we'll look at a couple more of these kinds of equalities and how they justify our pictures. Here we see if we group the wires together or if we group the different levels together and compose them, we get the same result. And this justifies us in simply drawing separate wires together and their own boxes without any groupings or parentheses. So this is kind of implicit in the language of pictures. So if we have any system that obeys these kinds of, you can compose in either way and it works, then that is well described by pictures. And so some more equalities, just to get familiar with these. We can slide the boxes along the wires. It doesn't matter exactly how we draw things as long as they're connected up in the right way. And some more examples of this intuition. If we swap around our wires, we can, again, just drag the boxes along the wires and unentangle them. And now for an application of these ideas in grammar, we can take a sentence and parse it, and grammar describes how the words connect together and how this creates a whole sentence. So if we think of the sentence, Romeo loves Juliet, we have the two nouns, Romeo and Juliet, and they're connected by the transitive verb loves, which takes a noun on the left and a noun on the right, and outputs a sentence. So one way of thinking of this string diagram we see here is that we input the Romeo and Juliet into the function loves, and out comes something of type sentence. And this kind of shows how the meanings, if you have a meaning for Romeo and a meaning for Juliet, you put those into something describing the meaning of loves, and you get the meaning of the entire sentence. And now, this string diagram that we see here for language is similar to one that we saw for physical systems in the very beginning with the pie. And it turns out that a linguist called Lambeck was attending a presentation by a physicist called Kuke, who was drawing how you show quantum teleportation with these kinds of diagrams, and he realized that they're the exact same structure. So with some work, they made some correspondence between these kind of grammatical parse string diagrams and quantum circuits. And so you don't need to understand the full details, just that there is a correspondence where you can take a mechanical procedure to take in a given grammatical parse of a sentence and output a quantum circuit. So we can make something like this. And yeah, there's a bunch of details which I cannot get into, but you have the same high-level structure of a string diagram in both the composition of meaning in the sentence and the operations that you perform on quantum systems. And so in this talk, I've described how monoidal categories formalize our use of string diagrams and how the kind of abstractions can reveal connections. And similar to what we saw in the previous talk, mathematics has previously been very successful in describing physics, mostly because physics usually takes a very reductionist approach, but then applied category hopes to be able to address the problem of compositionality more and possibly be able to describe more high-level problems, such as those in language or even social sciences. I hope you found this interesting. Thanks for listening.